Welcome to e-learning science. I am Dr. Mudasir, and today we will discuss a chapter which we call as carbohydrates. Although we'll be making series of lectures on this carbohydrate, but today in this video tutorial I will be discussing what is the structure of some monosaccharides and how we can write the monosaccharides, what is the structural formula, what is the presentation, and probably some functions also we'll be discussing in this video tutorial. Right. First of all, what are carbohydrates? As we all know, carbohydrates are the compounds of carbon, hydrogen, and oxygen. They are the compounds of carbon, hydrogen, and oxygen. And therefore, I can say they are organic. They are organic compounds. They are organic compounds. What are basically these organic compounds? Any compound having both carbon and hydrogen is considered to be as an organic compound. Those compounds which have carbon as well as hydrogen are considered as hydrocarbons. And what are inorganic compounds? They may have hydrogen. Inorganic compounds may have carbon, or they may have hydrogen but not the combination of both. They do not have the combination of carbon and hydrogen. So first point is carbohydrates are organic macromolecules. They are organic macromolecules. Again, organic we understand. What are biomicromolecules? Biomicromolecules means they are present in the biological system. And macromolecule is a molecule which is having a larger size, and apart from that the size is usually greater than 10,000 Daltons, and they are less soluble as compared to macromolecules. This is one more thing which we must understand. So my first point is carbohydrates are organic macromolecules. And if we see where these carbohydrates are present, they are forming the part of our cells. They are forming the part of our cell. If we see our cell, what is basically, if I will tell you what is our chemical composition, if I have to draw the chemical composition of any living organism, how I can draw it? Simply, I will yield the chemical composition in the form of carbohydrates, proteins, fats, lipids, and some minerals. That's all. So when we see the chemical composition of a living cell, living cell is made up of water. It is made up of proteins. It is made up of nucleic acids. It is made up of your we can say carbohydrates. It is made up of lipids, and it is also made up of some ions and minerals. If I compare the percentage of water in the cell is 70 to approximately 90%. And if we see the percentage of protein, it is the highest. It is the second largest. It is 10 to 15%. And if we see the composition of nucleic acids, it is 5 to 7%. And if we see the carbohydrates, it is 3%. And if we go to the lipids, it is 2%, and some ions is 1%. Here we are concerned more about this, that's carbohydrate. The percentage of carbohydrate present in a living cell is 3%. 3% of carbohydrate is basically present in our living cells. This is one thing. And suppose if I will tell you, sometimes we may just rearrange this thing. We may just make it simply a complex form of this. I will tell you, you just estimate the amount of carbohydrate which is present in a human being weighing 70 kgs. You have a question, 70 kg human being, we have a 70 kg human being, and I would like to calculate the percentage of carbohydrate. Very simple. I know carbohydrates are usually constituting 3%. 3% means 3 by 100. When I will do it, it is 210 divided by 100. It is 2.1 kg. So a person weighing 70 kg must be having 2.1 kg of carbohydrates, right? So my first point is carbohydrates are organic biomicromolecules, and carbohydrates are forming 3% of volume or 3% of the living cell, right? Then when we divide these carbohydrates, carbohydrates are classified into, carbohydrates are classified into, we have carbohydrates, they are classified into first thing and the second thing. Broadly, I can classify carbohydrates into two things. One is the simple carbohydrates, and second is the complex carbohydrates. We have simple and complex. In the simple, we have monosaccharides, and we have derived monosaccharides, and we have oligosaccharides. These are the types of simple carbohydrates. When we see the complex carbohydrates, in complex carbohydrates we have one category which we call as polysaccharides. And these polysaccharides are the these are the polymers. They are made up of monomeric which we call as monosaccharides. So we have simple carbohydrates, monosaccharides, derived monosaccharides, oligosaccharides, complex are also known as polysaccharides. Today we will be discussing probably monosaccharides. See, when we look towards monosaccharides, any carbohydrate, since it is made up of carbon, hydrogen and oxygen, any carbohydrate is represented by general formula CnH2nOn. CnH2nOn. For example, I will tell you when I have to just quote the definition of carbohydrate on the basis of on chemical basis. I can say carbohydrates are polyhydroxy, aldehydes or ketones. Polyhydroxyaldehydes and ketones. So carbohydrates are polyhydroxy. Polyhydroxy means it has number of hydroxyl groups. Aldehyde is represented by CHO. Polyhydroxy again means number of hydroxyl groups. Ketone is represented by C double bond O. Here we have a carbohydrate may be represented by aldehydic form, or a carbohydrate may be represented by ketonic form, provided it is polyhydroxy. It can contain large number of hydroxyl groups, right? So looking to this formula, when we see the monosaccharides are the simplest sugars. They cannot be further hydrolyzed. This is the basic unit of the sugar. Monosaccharide is the basic unit of the sugar. They cannot be further hydrolyzed. And looking to the formula, there are several types of monosaccharides. For example, if I will tell you, we have a formula which we call as CnH2nOn is the formula, and this N, so far as monosaccharides are concerned, this N varies from 3 to 7. And second thing is that, for example, if I will tell you what is the type of sugar, what are the types of monosaccharides which are possible. Number one, we have, when we will give value of N is 3. That means it is C3H2 into 3, it is 6O3. We call this sugar as triose. Then we have second, which we call as C4H8O4. We can call this sugar as tetrose. Then we have third one, C5H10 and O5. We will call it as pentose. We have, when C is 6, C6H12O6, which we call as hexose. And we have similarly the last one, that is C7 H14O7, which we call as haptose. This is the sugars, monosaccharides, which are various monosaccharides which are possible. And I told you monosaccharides are polyhydroxyaldehydes and ketones. Therefore, these triose may be represented by an aldose possessing the aldehyde group, or this triose may be represented by a ketose possessing a ketonic group. Therefore, we may have two things here. This triose may be in aldehydic form, which we call as aldose, or this triose may be in ketonic form, which we call as ketose. We may have aldose or we may have a ketose, right? When we see this triose, the simplest form of triose is glyceraldehyde. Glyceraldehyde is made up of, will be represented by the formula C3H6O3, and this glyceraldehyde is an aldose. It possesses aldehyde group, and in the ketonic group we have dihydroxy. The example is dihydroxyacetone. These two must be isomers because they have the same structural formula. Okay, so glyceraldehyde is an aldose. Dihydroxyacetone is a ketose. It will be represented by aldehyde group and it will be represented by the ketonic group. But the formula is same, that is C3H6 and O3. Then when we see the tetrose we have in the aldehyde form we have erythrose, and in the ketonic form we have erythrulose. Similarly, when we see the pentose sugar, the most famous pentose sugar is ribose. Sometimes we can write also deoxyribose, although it is not purely monosaccharide, but still I can write it deoxyribose. We may have xylose and we may have arabinose. They have all aldehydic forms. And here I have ribulose, the sugar which is present in ketonic form. A pentose sugar is known as ribulose. And so far as this hexose is concerned, we have glucose, we have mannose, and we have galactose. They all are hexoses represented by the general formula C6H12O6, and they all have aldehyde as a functional group. And then in this case we have fructose. Here we have in the haptose we have glycohaptose, and we have here pseudohaptulose. These are the examples of monosaccharides. The carbon atom varies from C3 to C7, and they may be represented in aldehydic forms or they may be represented in ketonic forms. When we discuss the aldehydic form, we have a glyceraldehyde, we have erythrose, we have ribose, deoxyribose, xylose, arabinose, and so far as the hexoses are concerned, we have glucose, mannose, galactose, and in the haptose category we have glycohaptose. Whereas representing the counterpart, that is the ketonic parts, we have dihydroxyacetone, erythrulose, ribulose, fructose, and pseudohaptulose. And let us see how this erythrose looks like. Let us see how this glyceraldehyde looks like. Let's see how this glucose, how we can draw the structure of glucose, mannose, galactose, fructose. We will come to these structures. For example, I will tell you. Let's start with the simplest sugar, that is glyceraldehyde. What is the prerequisite condition for glyceraldehyde? As I already told you, so far as glyceraldehyde is concerned, it has a formula. It is a triose. It can be represented by C3H6O3. It is a triose. And I know one more thing about glyceraldehyde. It is an aldose. It is an aldose because the functional group is, it is an aldose. The functional group is CHO. Okay, I will try it. How many carbons will you get? It is 3. It is 1, 2, and 3. These are the 3 carbons, right? And the functional group should be, it is CHO, aldehyde. It is the functional group, right? At position number 1, it is the functional group which is represented by CHO, aldehyde. And then we have polyhydroxyaldehyde. it means here it should be hydroxyl group, and here also it should be hydroxyl group. Then you simply balance the valency of carbon. It is 1, 2, 3, and here it is 4, that means we can write H. It is 1, 2, it is here we can write H, and here also we can write H. This is simply glyceraldehyde. This is glyceraldehyde. Now we want to see how the hydroxyacetone looks like. Again, dihydroxyacetone is triose, and it is represented by formula C3H6 and O3, but the functional group present in it is a ketose, and it contains ketonic group. So I can write it again, C3, 1, 2 and 3, right? Then I need to insert the functional group, and the functional group is ketonic, and here it is a ketone group. It cannot come at 1. It has always to be at position number 2. So it's C double bond O, it is a ketonic group. Okay, I have made the functional group. What I require else? I require the hydroxyl groups. Get the hydroxyl groups. You attach one hydroxyl group to this carbon, attach another hydroxyl group to this carbon, right? And then balance the valency of carbon. It's done. Well, balance the valency of carbon means it is 1, 2, and here it is hydrogen, and it is hydrogen, it is 4. It is okay, done. Then it is 1, 2, 3 and 4. Okay, already done. It is H and H. This is your dihydroxyacetone. Alright. Similarly, we can make other structures. We can make tetroses, we can make pentoses, we can make hexoses. Now, since I told you carbohydrates, monosaccharides have N which starts from 3 to 7. Okay. There are pentoses and hexoses. Pentoses and hexoses means N is the 5 and N is the 6. The pentoses and hexoses are not represented by open chain. They are more stable in a ring form. When I discuss the pentose, when I discuss the hexose, these pentoses like ribose, ribulose, xylose, arabinose, these hexoses like glucose, galactose, mannose, fructose, they can be represented by open chain also, but they are more stable in ring form. And the possible types of rings are, here we have two types of possible rings. So far as pentoses and hexoses are concerned, the possible type of rings are two. One is known as pyrenosic ring or pyrenose, and second ring is known as furanose. They are stable in ring form, and the possible rings are pyrenosic ring and the second is furanosic ring. Let us see how this pyrenosic ring looks like. This pyrenosic ring is a hexagonal ring. It is a hexagonal ring. Pyrenosic ring is a hexagonal ring. And hexagonal ring means it contains 5 carbons and 1 oxygen. It contains 5 carbons and 1 oxygen, right? Then if I want to draw it, this is like just like this. Right, okay. This is a hexagonal ring. Here it will be the carbon. It contains 5 carbons. Here it is a carbon. Here we have a carbon. Here we have a carbon and oxygen. How many carbons? 1, 2, 3, 4, 5. 5 carbons, right? And 1 oxygen. This is how I can write the pyrenosic ring. Let us go to the furanosic ring. The furanosic ring is pentagonal. It is pentagonal. It means it contains 4 carbons and 1 oxygen. Unlike this, it has 4 carbons, 1 deficiency of carbon, and 1 oxygen atom it has. 4 carbon and 1 oxygen. And I can write this is pentagonal, I can write it in this way. Since it is a pentagonal ring, I have to form a pentagonal structure for this type of ring. See, let me count. This is it has 4 carbons. This is carbon 1. This is the carbon second, carbon third, and carbon fourth. Okay, they are 4 carbons. And how many oxygen? 1 oxygen. So these are the 2 possible structures. One possible structure is the pyrenosic ring, and in pyrenosic ring we should note down that it contains 5 carbon atoms and 1 oxygen atom. And so far as the furanosic ring is concerned, furanosic ring has 4 carbon atoms and 1 oxygen. We can represent this ring by we can say by a pentagon, and we can represent the pyranosic ring by a hexagon, right? Now, this is true so far as carbon number 5 and carbon number 6 is concerned, so far as when the N is 5 and when the N is 6. That means those sugars who are pentoses and who are hexoses. Now again, there is one more thing. Sometimes we may call this ring as alpha pyranosic ring. Alpha pyranosic ring. Sometimes we may call this ring as beta. So pyranose ring may be exhibited in alpha form or beta form. Similarly, pentagonal, this furanosic ring can be represented in alpha form or beta form. We can write something, it is alpha something, alpha pyranosic ring, or we can say it is alpha furanosic ring, it is beta furanosic ring. How we can understand which ring is alpha and which ring is beta? For this, the oxygen atom, the carbon atom which is closest to this oxygen, the carbon atom which is closest to this oxygen, if the hydroxyl group is written below, if the hydroxyl group is written below, we have to see for the carbon which is close to this oxygen atom. If we will see the hydroxyl group is written below, we call it as alpha pyranose. Okay, so this is the structure of alpha pyranose. And else we can say, for example, if we want to draw the beta pyranose, then the hydroxyl group, the carbon atom which is close to this oxygen, if the hydroxyl group is at the above position on the top, we will call it as beta pyranose. And similar is the case of this thing. Let's come to this. We will see the oxygen atom, the carbon atom which is close to the oxygen. If the hydroxyl group is written below, it is alpha, and if the hydroxyl group is written above, it is beta. So this thing you should also understand. We may have alpha form or we may have the beta form. Okay. Then moving ahead, let's draw the structure of some pentoses, some hexoses, which is the main thing which we need to write, which we need to understand, and which we need to remember also, because they have the great significance. These monosaccharides have the great significance, for which we will be discussing also some in other lectures. Also, we will be discussing these things. Then let me make the structure of a. Let's go to the glucose first, hexose. When we discuss the hexoses, the hexoses may be aldoses, the hexoses may be aldoses, or the hexoses may be ketoses. Okay, ketoses. And so far as this aldose is concerned, we have the structure. We have in this we have the example of glucose, we have the example of mannose, and we have the example of galactose. Very important sugars. And so far as this ketonic group is concerned, we have the example of fructose. We have fructose. Now see, whenever this is C6, and C6, in the C6, let me see how is glucose. Let me draw the open chain structure of glucose. The glucose is an aldose made up of 6 carbons. I will write down the 6 carbons: 1, 2, 3, 4, 5, and 6. These are the 6 carbons. And the functional group for glucose is aldehyde. So I will write it is CHO at position number 1, right? Then it is polyhydrox. It contains hydroxyl groups. All the 3 have the same formula. Therefore, why is that all the 3, glucose, mannose, galactose, has the same formula, we can say. And all the 3 has the same functional group. That means it is aldehyde. Everywhere you will see these 6 carbons, you will see CHO also, right? So where is the difference there? How we can differentiate glucose from mannose and galactose? It is the arrangement of OH groups. OH groups, they must be differing in the arrangement of OH groups. Let's see. The OH group in case of glucose is here. You have to remember this thing. You need to remember this thing, and you remember glucose. The rest things will follow. The hydroxyl group arrangement is this, and at the last we have CH2H. This is the arrangement of hydroxyl group. Hydroxyl group is here. This is I just name it 1, 2, 3, 4, 5 and 6, right? Hydroxyl group is on the right side, it's on the left side, on this side, on this side and this. This is glucose. I have kept some valencies blank. Wherever there is any blank, it means we need to fill it with hydrogen. It is understood. We need to fill it with hydrogen. We have to substitute the hydrogen here. Wherever I find the valencies blank, it means I have to fill it with hydrogen atoms. This is what we call as glucose. This is your glucose. Okay. Again, we write D-glucose. D-glucose. We again write D-glucose. What does D means? D means the glucose is dextrorotatory. The glucose is dextrorotatory. Dextrorotatory or D or plus, something like that. Basically, the carbohydrates show optical isomerism. The carbohydrates show optical isomerism. What is optical isomerism? Here, this optical isomerism is the property of those compounds which have asymmetrical or which have dissymmetrical or which have chiral carbon. Chiral carbon means the carbon is attached to 4 different groups. The carbon is attached to 4 different groups. I can say I can say any carbon is chiral, any carbon is dissymmetric, any carbon is asymmetric when it is attached to 4 different groups. For example, this is a carbon here, it is attached to D, it is attached to F, E and A. This carbon is asymmetric, this carbon is chiral, and these compounds which have a chiral carbon have a property to show optical isomerism. They usually show optical isomerism. And all the optical isomers, how we can differentiate the optical isomers then? Optical isomers are those isomers, there are 2 possible isomers. One is D and second is L. What we are doing, if we put plane polarized light, if we insert the plane polarized light through these compounds, they may rotate it either to the right or they may rotate it either to the left. When the compound will rotate plane polarized light to the right side, we call them as a dextrorotatory. When they will rotate this plane polarized light to the left side, we call it as levorotatory. And the sugars are usually dextrorotatory. So therefore, I can incorporate a word, a letter D before beginning of the sugar. It means they show optical isomerism, and the type of isomer which they form is dextrorotatory. That is, they will turn the plane polarized light towards the right side. Okay, so we understand the meaning of D now. Okay, this is the structure of glucose, and I write it. Glucose is represented by the formula, the open chain structure which I have given, and it is D dextrorotatory. Then second is the mannose. Again, how many carbons we have for mannose? Mannose has 6 carbons. 1, 2, 3, 4, 5 and 6. Right? CH2H. The functional group is CHO. Right? And the arrangement of hydroxyl groups is same as that of glucose, except at carbon number 2. There is a change at carbon number 2. We have to look for the change, and the difference between the glucose and mannose lies at carbon number 2. That means this is let's see the glucose. It is CHO. This is carbon number 1. There is no change. At carbon number 2, there is some change. Okay, we will keep it as such. There is some change. Let's go to carbon number 3. It is H here. Okay, it is OH here. No problem. And let's go to carbon number 4. OH is on the right side. H is on the left side, correct. Let's go to carbon number 5, which is here, and H is here, no problem, right? There is a difference at carbon number 2. And what type of difference we have? The difference is in the arrangement of OH group. The OH group here was on the right side, but here it is on the left side. Here we have the difference. It was on the right side, and here it is on the left side. This is 1, 2, 3, 4, 5 and 6, and I will name it as, this is mannose but D-mannose. You understand why D-mannose, understand? Then we have one more thing which we call as galactose. Again, galactose has how many carbons? 6 carbons. 1, 2, 3, 4, 5 and 6, and the functional group is CHO, and here it is CH2OH. Let us see the glucose. For drawing, when we want to draw the galactose, again you have to take glucose as a reference point. The difference between glucose and galactose is only at carbon number 4. Rest everything is same. It means the carbon number 4 of glucose is here. There is a difference at carbon number 4. You just write just like this is carbon number 1, there is no difference. At carbon number 2 we have no difference. We can write just like OH and H in the same way as we have mentioned in case of glucose. Carbon number 3, no change. H is here and OH is here. And when we go to the carbon number 4, there is a change. There is a rotation. OH is on this side and H is on this side. So here we have a change. OH is on this side and H is on this side. And when we go to the 5, there is no change. 5 is same and 6 is same. So the difference lies here. It is 1, it is 2, it is 3, it is 4, it is 5, it is 6. The difference between the glucose and galactose is basically seen at carbon number 4, right? And I can write this. This is galactose. Galactose. Right? Now we have a question. What are epimers? What are epimers? Epimers are those isomers which differ in the arrangement of hydroxyl and H atoms around one carbon atom only. For example, if I have to see the glucose and I will see the mannose. What is the difference between glucose and mannose? The glucose and mannose have the same formula, but they have a little difference in structure, and the structural difference lies at carbon number 2. And what is the difference? At carbon number 2, they differ in the arrangement of hydroxyl and OH. They differ in the arrangement of hydroxyl and hydrogen atom. Arrangement of hydroxyl group and hydrogen atom around one carbon atom only, rest it is all same. So it means D-glucose and D-mannose are epimers because they have a single difference. They show the difference. They show the difference in the arrangement of hydroxyl and hydroxyl groups around one carbon atom only. So D-glucose and D-mannose are epimers. Let's see this way also. What are D-glucose and D-galactose also epimers? Yes, they are also. Because when we see D-glucose and D-galactose are epimers because they differ in the arrangement of hydrogen and hydroxyl groups around the carbon number 4. This is what we call as epimers. And I will draw fructose also. When we see the fructose, then ring structures we'll do again. We can take ring structures in another lecture, but we can see at least what is fructose, how we can draw the open chain structure of fructose. Okay, let's go to the fructose. Fructose is ketose. Okay, you understand ketose means it contains a functional group, ketonic functional group. And what is the formula? Formula is same. It is C6H12O6. C6H12O6 is the hexose. And how many carbons we have? It is 6. It is 1, 2, 3, 4, 5 and 6. You just make glucose here. It is 1, 2, 3, 4, 5 and 6. Okay, glucose we have CHO. It is OH here. It is OH here. It is OH here. You have learned it. It is OH here and it is CH2OH. Make every time give reference of the glucose always. You remember glucose, everything will follow. Then this we are drawing here the ketose. The functional group so far as this ketose is concerned is the C double bond O, right? Ketonic functional group. And here it will be CH2OH. Here also it will be CH2OH. Just like glucose here, it is CH2OH. But here we do not have functional group. We cannot incorporate the functional group at position number 1. Therefore, it is CH2OH. Rest, what I have to make? I have to make hydroxyl groups. You just put the hydroxyl groups exactly as you have put in the glucose. See, here it is 1, 2, 3, 4, 5, and 6 glucose. Here it is also 1, 2, 3, 4, 5, and 6. Alright? Let's see. Hydroxyl group at position number 3 is here. Hydroxyl group at position number 4 is here. Hydroxyl group at position number 5 in case of glucose is here, and also it is in case of fructose is here. And I have put some carbon as blank. I will fill the valency by substituting the hydrogen atoms. Here I can substitute hydrogen, but here I cannot. It is 1, 2, 3, 4. Already 4. Already 4. So this is your D. D means it rotates the plane polarity towards the right. It is D fructose. It is D fructose. This is simply how we can write the structures of sugars. If we want to draw the structure of ribose, for example, ribose is a pentose and it has a functional group aldehyde. Aldehyde functional group. Pentose means it is 1, 2, 3, 4, and 5. Alright? And it's a pentose, it has a functional group is CHO, right? And then you have to substitute the hydroxyl group. This is hydroxyl group, this is hydroxyl group, this is hydroxyl group. Here it is CH2OH. Then balance the valency of carbon, you know it is like this, it is like this, it is D ribose. D ribose. Right, I have also quoted one example, that is deoxyribose. Deoxyribose have one oxygen less. I cannot, that's not representing truly the monosaccharide. It's not representing truly the monosaccharide, but it is a derived monosaccharide. Since I have kept it here, but actually it has one oxygen atom less, though therefore it cannot be placed. It is not strictly a monosaccharide, but it is a derived monosaccharide. We'll be continuing the structures as well in the next lecture. Thank you very much.